Hello, so this is part 2 of our little series here on dealing with molar mass and molar mass of elements and how to deal with Avogadro's number and all that kind of good stuff. This little video should be relatively quick, I hope, and it has to do just with the kind of the next phase, which is using molar mass with compounds as opposed to with elements. In the last little video, we just did a couple of examples of how molar mass applies to elements. Remember that Avogadro's number has to do with the number of items that we're talking about, and that it also has to do with the molar mass or the atomic mass, if you want to think about the average mass of different elements. Well, good news is the same concept can be applied to compounds. That actually makes our lives quite a bit easier when we're doing chemistry. So when we're dealing with molar mass, when we do Avogadro's number and molar mass, there's a couple of things to know. I'm actually going to go back to this one really quick. That if we do 6.022 times 10 to the 23rd equals 1 mole, there's two different things that we can put in this kind of spot right here. If we're talking about an element, then we would say that this would be atoms. But if we are talking about a compound, then we can put one of two different things here. Usually with a compound, we would use this word, molecules. But I want to remind you that, especially if you're looking at your textbook or other higher level chemistry kinds of language stuff, the equivalent term to molecules is something called a formula unit. If I can write it here, formula unit. So what a formula unit, oops, no E on the end of that. What a formula unit is basically, it's a molecule of an ionic compound. Ionic compounds don't actually have molecules because the term molecule is only used for things that are covalently bonded. So when we're talking about an ionic compound, there is no such thing as a molecule of, say, salt, which is an ionic compound. So we would actually use the phrase formula unit. So in your head, the term formula unit and molecule should be the same thing, but technically they're not quite the same. So I just want to kind of mention that. You'll see that in the text a lot, that they use the phrase formula unit, and it throws students off. Like, what the hell is a formula unit? So basically it's a molecule. So for us, when we are dealing with Avogadro's number, when we're talking about compounds now, so now we can be talking about molar mass of compounds. And this is actually as simple as it sounds. So for this, you do have to remember your names and formulas. But if we want to know the molar mass of sodium chloride, which is NaCl, we would literally just go to our handy dandy periodic table and find our two elements that's on there. Sodium is 22.99, that's Na. And then chloride, Cl, is 35.45. And to find the molar mass of the compound, you literally just add them together. It really is that easy. 22.99 plus 35.45, it's 58.44 grams per mole for this particular compound. That many grams equals 1 mole of sodium chloride. Again, make sure that when you're doing your molar masses using the periodic table, you're always using 2 decimal places. That's the kind of convention that we use with these. So with some of these other more difficult ones, like when we're talking about things like aluminum sulfate or ammonium dichromate, now you do have more complicated formulas, but still it's the same idea. So aluminum sulfate, you should hit pause for both of these and see if you can remember how to write the formulas on these. I know you don't, you slackers. You don't remember how to write these, but maybe you do. So you should write the formula for aluminum sulfate and ammonium dichromate. Hit pause, do it. All right, aluminum sulfate. Aluminum and then sulfate, SO4, like that. This is aluminum, that's an L. Aluminum is a 3+, sulfate's a 2-, so we need to cross down. So it's Al2SO4 3. It's going to be big. Ammonium dichromate. Ammonium is a polyatomic. Ammonium is NH4. This is a 1+. Dichromate, by the way, is a 2. It's a 2. Dichromate, Cr2O7 is dichromate. Then to balance our charges, to cross it down, we would need 2 ammoniums like that. So when we do our molar masses for these, we literally just kind of add them up. And I'm going to kind of show you a little technique that will help us in a later step. So what I would suggest you do is kind of do this, Al, S, and O. Kind of list your elements out, N, H, Cr, and O. Kind of list them out in that sort of style, kind of vertically. Again, it'll make a later step that we do easier. Aluminum, finding it on the periodic table, 26.98 times 2. There are 2 aluminums in here. We do have to include both of those in the molar mass. Sulfur is 32.07. And now there's 3 sulfurs in this. Again, this 3 outside the parentheses does distribute across to both the oxygen and the sulfur, so times 3. And then oxygen. Oxygen is 15.997, or 2 decimal places, 16.00. Times, now again, we've got a 3 outside here and a 4 inside. That gives us a total of 12. So now when we do this, we can kind of add them all up together. And you can actually in your calculator just kind of enter it in like that. If you had a big calculator like this, 26.98 times 2 plus 32.07 times 3 plus 16 times 12. And we get this combined mass. It's a big number, 342.17. So sometimes students ask me, like, well, what about sig figs happens in this? These all had 4 sig figs. So I'll remind you of something. When you kind of multiply these across, the way that this will work and the way that we're going to do this with molar mass is this is actually addition. It's this plus this, 32.07 plus 32.07 plus 32.07 plus 16 plus 16 plus 16 plus 16 plus 16, etc. Remember, multiplication like this is simply repeat addition. And when we do addition, we maintain decimal places. So we will always do 2 decimal places. We will do 2 decimal places for the elements. We will also do 2 decimal places for the compounds. This now has 5 sig figs, but 2 decimal places is that key point. So again, I know that's a little bit of a picky rule, but it is based on the addition rule for significant figures, and that's how that comes from. So last one, again, you should probably hit pause and see if you can figure this out and make it work. And we'll do ammonium dichromate. So this is nitrogen is 14.00 times 2. Hydrogen is 1.01 times 8. Again, we've got 4 hydrogens times 2. Dichromate, chromium is 51.99 times 2. And then oxygen, again, is 16.00 times 7. So by the time you add all these guys up, 14 times 2 plus 1.01, enter my calculator, right? 1.01 times 8 plus 51.99 times 2 plus 16.00 times 7. And I get a total molar mass of 252.06 grams per mole. Would be the official units for these. This is grams per mole as well. So again, molar mass for compounds is simply the molar mass of the elements. Be careful writing your formulas. Don't forget to balance your charges, and then watch out for parentheses to make sure that you're actually distributing that number across. Okay, so using this in slightly more challenging problems is kind of the next step. Okay, I know you guys can add, but using Avogadro's number with molecules and with compounds, you can see that these problems are a little bit more difficult. So magnesium acetate is the example that we're going to use for here. Magnesium acetate is Chiku. I happen to remember that Chiku is a 1 minus, so magnesium is a 2 plus. So there is our particular compound that we're going to use for this. We're going to use this for all 3 of these. So how many grams of magnesium acetate, how many molecules are in there? So if we're trying to go from grams to molecules, we have to go to moles first, and then we can go from moles to molecules. So that's a second step that we can do. I will need to know what my molar mass is. Pretty much in all of these problems, you might as well figure out your molar mass is from the beginning. Magnesium is 24.31. Carbon is 12.01 times, okay, how many carbons are in here total? There's 2 carbons times 2. So that's times 4 is where I'm getting that from. Hydrogen is 1.01, and there are 6 total hydrogens in here. CH3, right? H3 times 2. So this is going to be times 6. And then our oxygens is going to be 16.00, times. There are 2 oxygens in here times 2 for a total of 4. So that's our total molar mass, 24.31 plus 12.01 times 4 plus 1.01 times 6 plus 16.00 times 4 gives me a total molar mass of 142.41 grams per mole for this particular compound. Okay, so how do we deal with this? So this is our wonder fraction time, right? This first one should be pretty easy. These other three on here are a little bit harder. So we have 76.99 grams of magnesium acetate, Mg, etc. Converting it, again, grams goes to the bottom. So we have grams down here and moles goes up here. This is a molar mass step. Whenever we have grams and moles, we use molar mass. So that's our 1.42.41 grams equals 1 mole. 142.41 grams equals 1 mole. Now we can go one step further because this one's asking us for molecules. And again, when we are using Avogadro's number with a compound, that means that our Avogadro's number tells us the number of molecules, not the number of atoms. So 1 mole of magnesium acetate, Mg dot dot dot, would equal 6.022 times 10 to the 23rd molecules, MOLEC, of that particular compound. So again, it's a big number, but this will give us the total number of molecules, not the total number of atoms. 76.99 times 6.022 times 10 to the 23rd, 10 to the 23rd, divided by 142.41 gives me a big number. And this is our number. We are at how many sig figs? 4 sig figs. There they are. So my answer in 4 sig figs, 3.256. It's actually 3.255626, whatever. So 3.256 times 10 to the 23rd. 23rd, this is molecules of magnesium acetate. That's how many molecules would be in there. So what about these other ones? These 3 other ones in here ask me how many total atoms, how many atoms of oxygen, or how many ions would be present in here. So I'm going to kind of keep this number, this number on here, up here, because that's going to be the basis for all of our other problems. So once I know how many molecules there are, I can do some other work with that. So I'm going to kind of leave that one up on my screen so that we can use that. That's how many molecules we have present. So how do we convert from molecules to atoms? Well, if you take a look at this, you got to look at your original equation or your original formula that's up here. If I want to know how many atoms there are, 3.256 times 10 to the 23rd molecules of magnesium acetate. Again, I don't have my label on there. All right, well, how many atoms are in each molecule? 1 molecule of this stuff has how many atoms on it? And you can do this as a conversion. This is not Avogadro's number. This is not molar mass. This is literally just taking this particular molecule apart. So what do we have in here? Well, I have 1 magnesium. Inside of this thing, I've got a couple of carbons. I have a couple of oxygens. I have a couple of hydrogens. And I got 2 of this whole thing. So how many total do I have? Well, let's look at this acetate. There's 1 plus 3 more is 4, 5, 6, 7 atoms are present in acetate times 2. So that's 14 atoms in acetate plus the magnesium gives me a total of 15 atoms in 1 molecule. And so if I just do this math, that will give me the total number of atoms that are present. And it's that 3.526 times 10 to the 23rd, 10 to the 23rd, times 15 will give us our total answer. If I wanted to do atoms of oxygen as opposed to total atoms, well, then I'm going to just take a slightly different version of this conversion. So this 15 atoms is total number of atoms. But what if I just want to talk about oxygen? So look closely. How many atoms of oxygen are in each molecule? Well, there's 2 atoms of oxygen in each acetate times 2 gives me 4 atoms. So I could literally do this. 4 atoms of oxygen is in 1 molecule of magnesium acetate. And I would do my math exactly the same way. So I can do either total atoms, look at everything and add them up. I can look at a specific atom and just say how many atoms of that particular element are present. Or I can do ions. And this is something we have not talked about in a while. So let me take a chance to kind of remind you how ionization works. And this is actually the process of dissociation. So I'll remind you, I'm going to do a simpler atom. If we have this stuff, NaCl, this is salt, right? When we dissolve this in water, it separates into 2 ions, sodium ions and chloride ions. So every molecule, formula unit, of salt, I would get 2 ions. Okay, well, what if we use a different salt? Okay, what if we use magnesium chloride? Magnesium chloride is this, MgCl2. When this stuff dissolves in water, again, this would be like a solid form, and these would be aqueous over here. When this stuff dissolves, I get a single magnesium ion and I get 2 chloride ions. It breaks apart into 3 separate ions. Okay, last step, kind of building it up to our magnesium acetate. So remember with polyatomic ions act like a team. They do not come apart. So we can actually replace the chloride in here. Sorry, I gotta get this separated out. We can replace this with magnesium acetate, CH3COO, 2. When this thing comes apart, we get a magnesium ion, Mg2+, and we also get 2 of these teams. We get CH3COO, an acetate ion, but again, there are 2 acetate ions. So for this, for every single molecule or formula unit of magnesium acetate, I get a total of 1 cation and 2 anions, or a total of 3 ions, like this. And that's important to us because that actually tells us something about conductivity, like how many electrolytes are present in that particular solution. So again, that's a little bit weird. Again, the math, I know you can plug in the numbers and chug it out. It's not that hard, but this is the example of how we can break down, use molar mass and Avogadro's number, but then break down, drill in even further to either number of total atoms, number of individual element atoms that are present, or number of ions. And with ions, you just got to remember how it dissociates. Again, polyatomics stay as a group. Just watch for your other subscript numbers that's on there. So there you go. That's it for today. Tomorrow, or this next video, we'll be dealing with percent composition, but you don't need to know about that right now. Okay, there you go. Have a good one. I'll see you in the next class.